Okay, I think we can get started. Some people are still trickling in, but let's start with class. We left off last week with, we learned about neural networks. We started with regression. We then went to classification, binary classification, and then we looked into deeper networks with more and more layers. And we saw how you can, stack layers, which are all weighted sums of the input of the previous layer, and then piped through some non-linearity, some activation function as it's called. And we saw how in this way you can stack layers with more and more parameters, more and more neurons. What we haven't talked about much and what we want to talk about now is loss functions. And loss functions are essential because your network makes some prediction, and ideally you want to predict the world as accurately as possible. But that requires you to measure the discrepancy. How far away is my prediction from what it should be? And this is, in some sense, the key challenge that we want to talk about here. Just a second, let me see. Yes. So we have inputs, we have a network, the network spits out some prediction, some output, and then we have to see how far is that from the target. And we need a way to describe how close the network's output is with respect to the target. And the idea is that this loss that we prescribe, it calculates a distance between the prediction of the network and the desired target. And so clearly the idea is that if you're far away from the target, then you have a large distance. If you're near the target, then you have a small distance. But that's kind of very simplistic, right? Because obviously if you think about it more, the unit of this loss function is essentially arbitrary, right? So proximity in this space often typically only has a relative meaning. Your prediction is close or far relative to something else. And one of the things we'll look at is how to optimize the prediction in the sense that we minimize that distance. And so this loss function aims at measuring the goodness of the prediction or the network's performance, if you will. And the large loss indicates bad prediction, and a small loss indicates a good prediction, but then obviously relative to something else. Maybe relative to the network before you trained it, or relative to some existing network. That's typically what we have in our community, that whatever challenge you tackle, someone has tackled it before. And they get some performance and you want to just be better than what the others have done. So often, the absolute measure of quality is irrelevant, but relevant is how good are you compared to the competition. And this choice of loss function is an important one, and it's complex. It depends on the concrete problem or the distribution of the target variable. So to give you some examples, so in this class we'll talk about it, throughout the class there's a variety of loss functions that will come up, so one aim of the class is just to expose you with some of the things that have been proposed in the literature, some of the popular loss functions. And two of the most popular loss functions are these here. One is called the L1 loss and one is called the L2 loss, or the mean square error loss, MSE loss. We've seen them before. Here they are again. So you have the prediction y hat I, and you have yi for a set of samples from 1 through n, say I equals 1 through n, and then you can either sum up the norm difference or you can sum up the squared norm difference, L2 difference. These are different choices of loss functions, and they have different behavior, different properties that they entail. And often this is a matter of, if you understand the problem you're solving, you will know which loss function you should prefer in what setting, and we'll see a bit more about that. We also talked about binary classification, this two-class issue cat, no cat, or cat or dog if it's only cats and dogs. Or here you have images you wanted, or some information on the internet you want to determine, is this fake news or not, right? So you want to devise some classification algorithm that can tell you, either given the image or given some text or whatever you want to classify. That would be an example of binary classification that can be quite useful with the internet flowing over with all sorts of claims and statements. You might want some AI system that can tell fact from fiction. And for these binary classifications, we've seen that we can use this binary cross-entropy, which looks a little bit complicated, but you remember how it came about. It's very much like throwing coins, where you have heads or tails at every time. And whenever you should have head, then the probability for head should be large. Whereas if you have tails, the probability for tails should be large. And then if you consider these as independent, then you have a product over all your samples. And then you have yi hat to the power of yi, and 1 minus yi hat to the power of 1 minus yi. And then if you apply the logarithm like we always do, you convert this product into a sum, and then you get the exponents come down. So you have yi times log yi hat, and 1 minus yi times log 1 minus yi hat. And remember, this looks complicated, but it's really not, because in practice the yi's are either 1 or 0. It's either object or background. Meaning if y is 1, you aggregate log of yi hat for that I, and if yi is 0, you aggregate log of 1 minus yi hat. That's pretty much all there is in this sum. So typically, in the sum for each summation, for each element in the sum, only one of the two terms is on and the other one is off. That is for two classes. And I don't think we've discussed how can we generalize this to multiple classes if we have more than yes or no, more than cat or dog. If we have 20 different animals, let's say here, and we want to say what's the probability that this is a dog, or it's a rabbit, or it's a duck, or whatever, right? Then you have a multi-class classification, and then an obvious way to generalize this binary cross-entropy to what's called the cross-entropy, in the case it's no longer binary, is that you introduce indicator variables, binary variables for each class. And so yik is a binary variable that is 1 if xi is in class k and 0 else. Right? So it's the same as that we had yi before, that was 0, 1. Now we have yik and y hat ik. And we sum over all the classes from 1 to some large k. So this is small k, I guess this should be large k, the number of classes that we consider here. And you can see it's very much the same, and the assumption is that every element can be in exactly one class. So in practice, if you sum yik over all k, you should get 1, meaning they're binary and only one of them is 1, in the sense that an image cannot be simultaneously duck or bunny. In this case, you could argue maybe this is both a duck and a bunny. But in principle, this is how you would generalize. And then this loss function that we have here is called the cross-entropy. And so it's the generalization of the binary cross-entropy to multiple classes. So we have the ground truth, y. We have the prediction of our network, y hat. We have a loss function that measures that discrepancy, could be mean square error, could be L1 loss, could be cross-entropy in the case of classification, or whatever other loss function. And in practice, you're often used to saying the distance between 2 points is just the length of the shortest path. But as you may know, even in the plane, there are multiple distances. You can take the Euclidean distance, you can take a Manhattan metric to measure distance, right? And if you get to more complex outputs of the network that are not just points, but more higher dimensional structures, then the question of how to measure similarity, how to define and compute metrics on respective spaces is a very fundamental one. And I guess you could do a whole lecture on metrics if you wanted to for science. How do you measure similarity between words? How do you measure similarity between images? How do you measure similarity between 3D shapes? How do you measure similarity between protein structures, right? So there is a multitude of things that we care about nowadays. Measuring their similarity is one of the most fundamental challenges in science. Just to mention that here. So it's not a trivial thing, and there's a lot of details. The devil is really in the details here of how you do these things. But let's say we have some loss function, and to start with, we'll often start simple, maybe some mean square loss. Then our aim is to minimize this loss, to train the neural network. Often people talk about training networks. What do they really mean when they say train a network? Well, you have a loss. You want to find a parameterization of that network that minimizes that loss, that makes the best possible predictions. And so minimizing the loss is the way to get to better predictions of the network. And finding better predictions amounts to finding better neural networks. And so the idea is that we initialize a network somehow, we get some prediction that is possibly very bad initially, and that has a fairly high loss, and then with time we train the network, and during training, over training time of the network, the loss gets smaller, the predictions get closer to the desired target. And then what you can do in training time, and this is often a very useful thing to evaluate progress in training, is you plot your loss. You start with the initial loss you computed, and over the course of training, you plot the loss. And ideally, you should see something like that. And if you don't, then there's something fishy in your code, right? That's a pretty obvious thing. If the loss goes up, if it oscillates, something is not right. And you might have, with time, intuitions about what is not right that would help you to debug your code. Most likely the learning rate is not chosen appropriately, for example. We'll come to what the learning rate is. So then, as a function of the parameters, right, so this is my unknowns, the parameters of the networks, that could be the weight matrix W or the biases, or maybe you have unknowns in your activation functions. If it's parameterized activation functions, we've seen you can do that as well. So there's all sorts of parameters to your learning problem. And then as a function of these parameters, you can plot the loss, the discrepancy between the prediction of the network f theta with these parameters and the ground truth label y that it should be. And so you have a loss, and in principle you can have that for every training sample, or you can plot it for all training samples jointly. So you have a loss. And the question is now, how do you find the optimum? That is, this set of parameters theta that gives you the smallest loss. So this is a challenge of optimization, and this is usually what optimization is all about, finding minimizers. And you remember that from high school math, right? That, you set the derivative to 0 at the minimum. The derivative with respect to theta should be 0, and you can try to solve that equation. That works if it's a quadratic loss function, right? Then you can set the derivative to 0, you get a linear equation. We've seen that in this class even. That's very nice and all, but for real world problems it doesn't work, because you have millions of parameters and your loss is neither quadratic nor even convex. It's very random in a way, very complicated, let's say. And so just setting the derivative to 0, you get a super complicated equation that you will not be able to solve. And so this is typically not a way to go. And so what we typically deploy for large-scale optimization as the default method of choice is a technique called gradient descent that will start somewhere, maybe here, with a parameter value theta that gives you some loss, and then ideally you go down the hill until you can't go down further. And then you go with that solution. And you can see already in this schematic drawing, if you start on the left and go down the hill, you'll find the global optimum in this picture. If you had started from the right, you would have found a different solution, and in fact a local optimum, and that is typically all you can expect in a non-convex optimization problem. You will never typically get better than a local optimum. And the question is how to go about this. But this is, for now, besides the points, we'll start with how to actually compute the gradient descent, how to compute local minima. You can see another thing, by the way, the whole gradient descent builds and hinges on the assumption that your loss functions are what's called differentiable, that you can compute derivatives. And we'll see how that can be done. So we have the loss function. We want to find parameters that minimize it. So we want to minimize this loss as a function of theta. And so I've changed the slide a little bit to make it very clear, because this is possibly one of the most important technical slides in the whole class. This is the slide that introduces gradient descent. So please pay attention now, in case you haven't done so yet. Here's the loss function. Here's the minimum, the theta star that we're all looking for, the optimal set of weights that gives us the best predictions with respect to the ground truth. But we initialize somewhere, let's say some at time t, we're here somewhere, and now what we want to do is we want to get closer to the minimum. How would you do this? You know, let's say you're in a landscape and someone tells you to go to the lowest point of the landscape. How would if you spill water, it goes down to the lowest point. How does it do so? Well, at any point, the water forms a way that just goes downhill, right? So you would look around, which is the way down, and you would take a step in that direction. Now, obviously, in the Dolomites, please don't do that, right? You would kill yourself instantly if you take the steepest way down. But hey, it would get you down, right? You might not be alive at the end, but you'd be down, right? And so here, the analogy only carries so far. Humans don't usually take the steepest descent, but here we do. So here, what tells us the direction of descent is the gradient vector. We'll come to that a little bit more. It's a vector, the derivative with respect to all the unknowns as a long vector, and it is a vector that points in direction of the steepest ascent. So it tells us in which direction does the loss increase most. And so what we do is, as you can see here, iteratively at each time step from t to t plus 1, we update the set of weights by taking the old set of weights at time t and taking a step in direction of this negative gradient, because that is the descent direction. The gradient points uphill, the negative gradient points downhill. It is the direction of steepest descent. And then this is weighted by a parameter alpha that is commonly called the step size in gradient descent. But in the neural network community, they rename everything, and so it's called the learning rate there. It's the step size. And why is it called learning rate? You can imagine if you crank up the parameter alpha, it's some scalar weight, it tells you how big a step you take in the downhill direction. If you increase that weight, you will do larger steps. And so the learning rate is increased. Now you'd say, hey, great, why don't I increase it to infinity to get the super fastest learning algorithm? Yeah, you can see in this picture what's going to happen, right? The next step should get you here, somewhere towards the minimum. If you take a too large alpha, you will jump beyond the minimum, and then you will see things will start oscillating. And then if you plot the loss function, it will not be going down, but it might actually be going up, right? And then you see something is fishy, and then that might be an indicator that your learning rate is too large. And so you need to choose it appropriately. What is appropriate beats me. There's gazillions of scientists over centuries that have wondered how to choose the optimal parameters, alpha, the optimal step size for gradient descent. There is no one solution fits all. There are lots of strategies, lots of heuristics that people have cooked up over the years. And most of them, I find, you can cook them up yourself if you think about it for 5 minutes, right? When I started implementing my first gradient descent, we didn't have Wikipedia at the time, so I just did trial and error, and I came up with, adaptive learning rate schemes. And years later, I learned that they all have names and that they're known in the literature. But they're just, heuristics. You take a step, if your energy goes down, next time around you take a slightly larger step, meaning you're optimistic. Last time it worked, let's try it again this time. If it starts oscillating, you reduce the learning rate again. And this is, I think it's called the Armijo rule or something, not sure. I don't think he got a Nobel Prize for it. It's a pretty obvious idea. And there's other techniques. You can do line search, where you basically evaluate for different step sizes in that direction, the loss function, and you take the one that gives you the lowest loss, right? And if it's a one-dimensional problem, because once you choose the downhill direction, then you can sample along this direction the loss, and you can just take whatever is the lowest value. That's probably a pretty clever idea. So that's called a line search. And so all of these strategies that you could easily come up with, if you spend more than 5 minutes thinking about it, they all have some names. And they're being used, and which technique you want to use in which setting, this is a little bit, up to you. And a lot of the software packages for deep learning, they come with a zoo of heuristics that are already integrated. And, you can take it or leave it, right? But ideally, this is the update of the gradient descent. It's very simple. At each iteration, take the old way, do one step in the negative gradient direction. And then iterate that, right? So then you take t going to infinity, and ideally, if you keep iterating, you end up at the minimizer, at the optimum, the local optimum, one should say. To what extent that is guaranteed is another question. That depends on the choice of learning rate, but you can prove that if it's sufficiently small and the loss function is sufficiently smooth, then this will get you to a local minimum. Say what? Whether you should go through the whole graph. So this is a good question. This strategy would get you, if you start from the left, it would get you to theta star. If you started from the right, it would get you to the other minimum there, right? Now you can say, well, what can I do if I don't know where the truth is, in the real world, you cannot plot the loss function. I mean, if you can plot it, you can see the minimum, then you're done. But let's be honest, in deep learning challenges, you have millions of parameters. It's not a 1D line and a loss. This is a very abstract visualization. So this dimension here has hundreds of thousands of directions, right? And you can no longer plot and visualize the loss function. It's hopeless, right? And so you don't know where the minimum is. So, you can initialize somewhere, do gradient descent, keep your fingers crossed that you get something reasonable. What you can do, though, you can see it here already, you can do the same thing with different initializations. Obvious idea, not very deep. That's what people do, yeah. They do different initializations, and they do gradient descent from there and see how it works. But can you guarantee that your algorithm will find the globally best solution? No. You cannot. And to date, this is an open challenge. And why it works to date is a little bit not fully understood, really. But I mentioned it last time, this is one of the main reasons why people went to deeper networks. The predictive power is not larger with a deeper network, but somehow the solutions you find seem to be better. And this was the biggest mistake of the neural network community in the 90s. I remember it. I was there in the 90s. People had shallow networks. They had one hidden layer, and they had a theorem that said with one hidden layer you can approximate any decision boundary arbitrarily well. Meaning there exists a set of parameters with one hidden layer that can encode any decision boundary. It exists, but can you find it? That was the real question. And in practice, you typically would not find the optimal solution. But then with deeper networks, somehow people were able to find much better solutions. And my colleague Burkhard Rost, who is here, who worked a lot in the 90s on neural networks, he said they didn't realize that going deeper would help you getting better solutions. And that really then created the breakthrough of the deep networks, that you get better solutions. And is that provable? To my knowledge, no. It's a heuristic observation that with deeper networks, somehow you get better solutions. So how do we go about this? We have inputs, we have targets, we have a neural network. Say if it's a one-layer neural network with no activation function, so very simple, just linear transformation with a set of weights. And then later we'll have a bias as well among the unknowns. Then we can take a loss function, let's say here the mean square loss. And then given this loss, we can try to optimize with respect to the parameters theta, that in this case are just the weights of the matrix W. Then we saw this last time, we can introduce these compute graphs that allow us to encode the loss function in a graphical way, and that allow us first for a given input, we can do a forward pass in order to compute the loss. And then we can do a backward pass in order to optimize the parameters. And so in this case, we multiply the input x with the weight matrix W, and then we compute the loss with respect to the label, the ground truth y. And then the idea is that from the loss, we can do a gradient flow to compute the update on the weights. This is how it would look for a simple task with a linear function and a mean square error loss. In neural networks, we typically have multiple layers, we have non-linearities, so things are a little bit more complicated. But here, what we can do is we can define f. We can then do a gradient. So the gradient is the vector of derivatives with respect to theta, all the unknowns, so these W, and this is what it looks like. And so then that would allow us to do a gradient descent, so to do an update of the weights according to this gradient vector. And we would always step in direction of the negative gradient. Once we have multiple layers, things are more complicated. Then, as we saw, we always have a nesting of multiplication with a weight matrix, Wi, and then some activation here, this ReLU, the truncated linear, rectified linear, it's often called. And so what we need to do is we need to propagate the gradients from the first layer all the way back to the first layer. So from the end, from the loss, all the way back to the first layer. How would that look? So here we have this for one layer, right? So we have a multiplication with weights, then we have an activation function, and that then feeds into the second layer where we have another set of weights, W2, and then we compute the loss, let's say the mean square error or something with respect to y. And then along the same way, and then there is a dashed line you see in this graph. This dash signifies that in principle you could have multiple layers stacked in the same way. So you could stack them all and ultimately then have the loss measuring discrepancy to the ground truth. And then you need to compute gradients with respect to all weights. So not only the weights of the first layer, but also the weights of the second and third, etc. layer. And we need to compute these gradients in order to update the weights according to the gradient, to the negative gradient. And then we can do that by propagating the discrepancy. So any discrepancy in the loss will entail some update of the parameters in the weights. And so we'll see a little bit more in the coming lectures how we can compute gradients per node, how we can do this recursively from right to left using the chain rule. And this is called backpropagation learning. So as I mentioned, the neural network community has a tendency of renaming things. So, you know, much like the step function in gradient descent is called the learning rate, the gradient descent with a chain rule is called backpropagation learning. And so you have this network with multiple layers, with multiple weights, and then you use this technique that we'll see that's called backpropagation, that uses the chain rule to compute the gradients. And for that, compute graphs really come in handy. When you first see compute graphs, I should say they look a little bit threatening because even very trivial expressions, you saw it already, get very, very complex graph structures or very, big graph structures. But it turns out these graph structures can make the implementation of the gradient descent fairly easy. And once you basically encode your loss function and your overall optimization problem as a compute graph, it basically gives you a standard recipe to do optimization, to do backpropagation learning. Now, why gradient descent? Why do we use that technique over other techniques? One should say the optimization literature has a multitude of techniques that people have cooked up over centuries, one can say, to minimize loss functions. And gradient descent is possibly the most simple, most naive technique there is. There are more sophisticated methods. Some of you might be familiar with them from other classes. There are so-called second-order methods that not only compute the first derivative of the loss, but also the second derivative. Why would you do that? Well, if you have a loss function that is so, and then you want to get to the minimum, we saw with gradient descent, one issue is you can say which direction does it go downhill, this direction in your loss landscape, theta, right? But you don't know how far to step. And one technique that is called the Newton method, what it does is it fits not only the first derivative, that means a tangent, but it fits the second derivative, which means essentially at your given point, theta t, you fit a paraboloid, right? Something like that. That is basically coincides in terms of first and second derivative with the function here. And so you have a paraboloid. Once you have a paraboloid, what's nice about a paraboloid, you can analytically find the minimizer of this paraboloid. So the theta t plus 1, you take as the minimum of that parabolic fit. And then you go here, you fit another paraboloid, and you can see how very quickly you get to the minimum. And this is called the Newton method, this idea. It's a method that uses not just the first derivative, but also the second derivative, and iteratively fits paraboloids in steps to the minimum of each paraboloid. Because the minimum of the paraboloid, if it's positive definite, you can solve that. It's a quadratic, right? So it's a linear equation that governs the minimizer. That can be solved analytically. Matrix inversion, you get the minimum. All nice, all good. What are some of the issues? Why do people not use Newton methods for minimizing deep networks? If they are so much faster, they are much faster if you can apply them. Why would people not apply a Newton method? Yes? Exactly. You pointed out the two big problems. They need to be twice differentiable. Right? That's already a big assumption, and these loss functions are highly non-differentiable in a way with these activation functions that have kinks, etc. But also, as you pointed out, you have to compute the Hessian matrix and then invert it. Good luck with that. If you have millions of parameters, you have a matrix that has millions times a millions, and then invert a matrix with a million times a million. That's pretty hopeless, right? So people have tried and people are trying because, you know, this is my experience. Scientists never give up on things, right? So there are people as we speak who try to develop adaptations of Newton methods that will hopefully be able to train neural networks. And there's, you know, it's not impossible, I would say, that eventually someone comes up with some clever strategy to do it. And there's a lot of, you know, other techniques, adaptive moments, conjugate gradient methods. In this class, however, as most of the deep learning community, it's an introductory class and it's not really so much an optimization class. So we'll not dig very deep into this and we'll focus more on gradient descent because that is what people currently use and that seems to work. Sometimes if the network is big and you don't have endless GPU resources, you might be spending weeks to train it. But, you know, unless someone comes up with a more clever algorithm, that's how it is, right? So to summarize this part, neural networks can be represented as computational graphs. And these computational graphs give us a way to feed forward, to do a forward pass, to evaluate the loss for a given set of parameters. But as we will see, they can also be used to backpropagate and optimize the weights with gradient descent. And as we'll see, we're using the chain rule. And why is the chain rule an obvious choice? Well, because your weights are nested in there, right? If you look at this expression, you know, this is your function, then you have the loss that measures the discrepancy of that prediction f with respect to your ground truth. The unknowns are all in orange, they are nested inside there, so you need to do chain rule to compute derivatives. So it's, you know, there is no other way to do it. And as we saw, optimization can be done using gradient-based solvers, and we'll look more into that in the next slide deck. And gradients we saw are computed using backpropagation, and this is nice because it can easily modularize and be deployed to very complex network architectures, because that's important. You know, we don't have a standard mean square error quadratic loss function. No, we have fairly complicated loss functions, and you want some technique where, you know, I give you my loss function and you can just off the shelf deploy it and train it, right? And this is where this compute graphs and the backprop learning comes in handy. And so this is what we'll look at more closely in the next set of slides. So that was this part. That brings me to part 4. So I apologize that, as you can see, for now the slide decks are not fully synchronized with the lectures, but I think that's not a disaster. Rather than changing the slide decks, I will just go as it is, and maybe we'll somehow make up. So optimization and backpropagation learning, recap, we have a neural network, with a set of weights, and we saw that for small networks with a small set of classes, each line of the trained network represents, the average car, the average bird, the average cat, and at least for some classes, like the horse class, you can roughly see, a brown horse-like shaped object on green background seems to be dominant. We saw that once the data sets become bigger, like ImageNet, and have millions of images and thousands of classes or hundreds of classes, then things get more complicated. And especially if the horse isn't always in the same orientation, in the same location of the image, then it's much harder to see anything in the first layer. So we saw we need more layers to have a better representation, to have non-linearities that we can represent. And we saw that we need both matrices with additional unknowns, with additional weights, but also activation functions that create non-linearities, because if we didn't have activations in between, we would just have a multiplication of matrices, and if you multiply 2 or 3 matrices, it's still a matrix, so you wouldn't gain any expression power. And this is why these activations here are in between, either the ReLU, this max 0 W1x, or the tangent hyperbolic or whatever else, or the sigmoidal. There's lots of different activations. We saw that. Then we saw that we can, so this way we extend the one-layer network to multiple layers, and we saw that we can visualize this graphically in this fashion, or with bigger networks in this fashion. What you see here is that in these examples, each layer has the same number of neurons. This is obviously not required. You can have different number of neurons in each layer. And typically, I didn't mention that, but the number of layers here, this is referred to as the depths of the network, for obvious reasons. Whereas the number of neurons in each layer is called the width of each layer. And here in this example, all layers have the same width, but they can have varying widths. And sometimes you want to introduce layers with smaller widths that, that boils information down to fewer neurons, and that in some form compresses information. And this is typically the strategy to bring in invariance, because then the network is forced to compress that information to a smaller number of neurons, and that way invariably kick out kind of redundant information. For example, if you want a horse classifier, something that more or less disregards the background, right? Because it's still a horse no matter what background it is on. And you can do so by compressing things to smaller layers. Here are some of the activation functions. I believe we've seen them before. The sigmoid, 10H, ReLU, and some parametric functions where you even have parameters that you can optimize so as to maximize the performance of the network. And we'll actually go into the choice of activation functions later in class. What activation function has which properties and when would you use which function. For now, this is good. We have loss functions. We talked about different loss functions. L1 loss, this mean square error loss, the squared L2 loss, the entropy or cross entropy, binary cross entropy and cross entropy loss for classification. We also talked about this idea of compute graphs, that it has nodes, that it has edges connecting the nodes, and a directional flow, how information inputs are processed in the network, and then you would backpropagate through this to train the networks, and this is what we're going to talk about now. We already mentioned the gradient. So you compute gradients, and I'll come to the exact definition of the gradient in a second. The problem is, in practice, you would like to compute the analytical gradient and then maybe set it to 0. At the optimum, it should be 0, right? But this is often too complex to compute. And so you typically break down the gradient computation layer by layer. And this is where this layered representation that we have in neural networks comes in really handy, that it can do the processing layer by layer, and that, also the training can be done layer by layer, and propagating this information both in the forward and the backward paths can be done very efficiently and can be done on, for example, GPUs. The unknowns here, the theta, that typically refers to the weights and the biases in all layers, right? But as we saw, it can also involve other unknowns, like in the activation function, you can have parameters that you want to optimize for. And this strategy that breaks down the gradient computations layer by layer is called backpropagation. And so this is what we'll discuss now. Here's the idea for, again, first we start with a simple expression, x plus y times z, super simple. But you see already for such a simple thing, we get a big graph, computational graph. So how do we use this graph now? We can use it in the forward pass. And this is, we set some initialization, say 1, minus 3, and 4. And then we can, layer by layer process. 1 minus 3 gives minus 2. And then 4 from z, and the multiplication of this gives us minus 8. And so this is how we can evaluate this expression. And obviously, any more complicated expression can be evaluated with a similar graph. Now, what we're interested in is computing gradients. Why are we interested in these? In particular, because maybe we want to optimize the unknowns, right? So we want, let's say, if these are weights or something, we want to optimize the weights, and so we need to compute the derivative of the output f of this expression as a function of x, y, and z as a function of these unknowns, or the variables. And in practice, at the end, we have f, so we start with df by df. This is typically 1, is always 1, not typically. And then we go back through this, in this backward pass, we say what is df by dz. That is, as you can see, d. And so here we just have, and d, as you see, is minus 2. So we get minus 2 as the derivative, so this is the derivative of f with respect to z for the given set of entries, right? And so we have minus 2 here, and along the same vein we can do df by dd. This is this intermediate value. D is the sum of x and y. We call it d. So as you can see, whenever we have a processing, we add an additional variable here to encode the output, and that is our d. And df by dd is z, because f is d times z. And so this is z, and so that basically gives us the 4, because z is 4. And then we have df by dy. Df by dy is just 1 times the 4. So we did df by dd, and then this is df by dy. We take the 4 that we have here and multiply with dd by dy, right? So here you see the chain rule. df by dy is df by dd times dd by dy, right? And so this is the 4 times dd by dy is 1. Right, so this is 4 times 1 is a 4 here. And so this is what we get as output here. And along the same vein, we can do df by dx, which is df by dd times dd by dx. And so this is the 4 times the 1 here, so that gives us the 4. And so in this way, you see, we can iteratively compute derivatives by chain rule, and we can do this on the compute graph by storing, every time we hit a new node in the compute graph, we can store respective derivatives and then just keep multiplying them with the previous expression. So we start with the 1 times 4 times 1, and then we end up with this, right? And this looks very complicated, but it's really a standard recipe that can be easily implemented in a machine. So we can now apply the same idea of backpropagation learning to train a neural network. And the neural network has a number of unknowns. N here is the number. So we have, L layers. L is the number of layers. M is the number of neurons in each layer. And N here is the number of inputs to each neuron. And then these weights can have indices L, M, N. So that is the weight that weights the mth neuron in layer L, and that is multiplying the input N, right? And so this is a set of weights here. Then we have, and we could have respective biases as well. But for now, I think initially we'll leave out the biases. We'll just focus on the weights. And then we have the prediction y hat, and yi is the ground truth, and L is the loss function that measures the discrepancy, for example, in a mean square error fashion, if you will. So here we have an L2 loss. So this would be a very simple neural network, 2 inputs, and then 1 output, and then you have a class label that it should agree with ideally. So a loss function that penalizes this discrepancy. And this very simple network architecture leads to this compute graph, right? So x0, x1 are the inputs. They're multiplied by weights w0, w1, summed up. That gives you the output, and then you take that output, subtract y0, the desired the target label, and then you square this to get an L2 loss on the discrepancy of the weighted sum minus y0, right? So, it takes some time to get used to what these compute graphs look like, right? Typically, each time you do something, you will have to add a node to your compute graph. You sum up the weights, you multiply the input with the weight, that is one node, then you sum up is the next node, then you subtract y0 is another node, then you square the whole thing is another node. And so that basically encodes your optimization problem. And now the backpropagation propagates that loss, discrepancies in the loss, back to the weights, right? So what we care about in this case are the derivatives of the loss with respect to the unknown weights, here W0 and W1. The 2 weights that these 2 inputs are weighted with. This is an L2 loss. In the case of a logistic regression, things are a little bit more complex. So here we make this 3-dimensional. So here we have a regression or classification, classifying a 3D output in Y. So here you see the network architecture that we consider and the corresponding compute graph on the right. And so what you have here is you have 2 inputs, and there is 3 neurons, and then there is 3 outputs, let's say for 3 different classes, if you will, right? And then you have a ground truth label for each. And how many edges do you have here? In this case, since you have 2 inputs and 3 outputs, you have 6 edges, so 6 weights that you need to optimize. Typically, we talked about these indices here, W00. This is basically the first zero is the number of the weight, and the second is the neuron, and the second is the input that it weights here, the input from 0, and this is the first neuron, but weighting the input from X1. Still a one-layer neural network, but with 3 outputs, as you can see here. And you can see very easily these compute graphs grow rapidly. Yes? Why is it always what? Oh yeah, so I should, yes, I think this is probably Y1 and Y2. You're quite right. Yeah. Because we're measuring discrepancy to Y0, Y1, and Y2. Yeah, good point. I didn't even see that. Yeah, there is a mistake in the slides. I believe this should be Y1 and this should be Y2. Thank you for pointing that out. Here, X is the input. This is the input, and then we have weights that are encoded here. They're not seen, but they're on the edges. Whenever you have edges in your network architecture, that each edge corresponds to one weight. And what we're optimizing is the weights. So we want to classify or regress on some input, and we want to achieve some output here. Now we add the activation functions. So, in a single layer neural networks, we would have weights, biases, and then we'd have the activation functions here. So this is the loss function. So this is the prediction of the network in a given layer. This is the activation applied to the weights multiplied by the input plus the bias. And this is what it would look like, and there's a computational graph associated with it. And here you would have different losses, and typically the overall loss would be the sum of a set of losses. So for example, you could have a loss for each I as yi hat minus yi. And then the total loss would be the sum of these losses. And then the chain rule would basically say you need to compute the derivative with respect to a set of weights. So you first compute the derivative with respect to the prediction of the network, and then the derivative of how does the prediction depend on the weights, right? The usual chain rule of differentiation. But in practice, you would do this both for the weights and also for the biases, obviously, to optimize both the weights and the biases. And then this is what this could look like. So here we add this activation function, this one here, this sigmoidal one, right? In this case, how does that look in the compute graph? Again, things look a little bit, it takes time to get used to how to convert a mathematical expression to a compute graph. This is something that needs some practice, but you can see here, it's not difficult, but it takes some time to get used to it. Multiplication with weights, summation with a bias b, then I subtract 1, right? And then I exponentiate. Sorry, not subtract 1, but you see it here, multiply with minus 1. This is what I do here. So this whole expression is multiplied with minus 1, then it's exponentiated, then I add 1, and then I do 1 over the whole expression, right? And this is what this looks like in the compute graph. So not profound, but takes some time to get used to, and to see that what you have here is nothing but the sigmoidal function applied to the input. And so this is something that we'll do in the exercises a lot, that you get experience with writing expressions in form of compute graphs, doing forward passes and backward passes through this compute graph. And we have some examples here in the slides, but they're somewhat illuminating. So for this, for example, you can see what does a forward pass look like. So here's a set of initial configurations. They're just random: 2, -1, -3, -2. And then you can do the computes, you can multiply, you can add, you can propagate this through, and then you get some output of 0.73, let's say, right? And that would be then the output of the network. And now you want to optimize that maybe with some loss function, and want to optimize the weights accordingly. And how would you do this? Then you would, for each term in this compute graph, the 1 over x, for example, the summation, the exponentiation, the multiplication with, say, -1 here, right? This alpha times x. You compute the derivative at each node of your compute graph. And this is quite standard. You know what the derivative of 1 over x is -1 over x squared. The derivative of the summation with alpha is just 1, because you're taking derivative with respect to x. Exponential function, the derivative is the same as the function itself, and here you get alpha. So far, so good. So once you've written that down, now you can do the backpropagation. And so again, you start with a 1 on the right, the function as a derivative of the function, the output f with respect to itself is 1, and then you propagate this in, right? So here, for example, in the first step, you would say 1 times, you take this 1 times the, why do you take, you would take the derivative with respect to, the derivative here. So this is dg by dx, evaluated at x, and here x is 1.73. That was the x here, right? And so this is from the forward pass. We know what x is coming in, and so we know what the value of x is. We can plug that in here, get 1.73 minus 1 over 1.73 squared. We multiply this by 1, we get minus 0.53, and then we can do that, for the next node. This is the plus 1. That's this node, and we see for the derivative of this plus 1, derivative is just 1. So that means we just keep the minus 5.73, multiply by 1, we get the minus 5.73. And then here we are in this node where the exponentiation, so we have the exponential function of x. What is x here? We can read it out. X is minus 1 here. And so we have e to the minus 1 times the minus 5.73, and that gives us roughly minus 0.2. These are just, rounded numbers. In practice, you'd have to maybe store the exact numbers. And so you see how we can compute the numerical gradient and propagate it down the chain. And this is essentially the idea of backpropagation learning, such that we have finally computed the backprop through the computational graph that represents our network. And this is in fact a very good exercise for you guys. Take a random network architecture, some mathematical expression, write it down as a computational graph, do forward passes, backward passes through the network. And so that allows us now, we have found a way to compute partial derivatives by propagating this information from the output back to the weights. Now the question is, this allows us to compute derivatives. How do we make use of them? And so here you see the outcome. If we keep propagating this, I can compute the derivative of the output with respect to the weight W1, and that is minus 0.2. And with respect to the other, to B, it's 0.2, for example. And here the other weight is minus 0.4. In practice, you only care, as I said, about the derivative with respect to the unknowns. The x are the input to your network, the w's are the unknown weights in this case, and the bias b as well, right? That's the three things that you care about where you want to compute the derivatives. Now we have these partial derivatives. Now we can do gradient descent. So we want to minimize our loss function, and I apologize for a slight change in notation here. Here we have some expression f that we want to minimize with respect to x. Right, so our unknowns in this case are x. Forgive me, it should be theta and b and whatever your unknowns, right? But let's just keep things simple. In the literature, typically when you introduce gradient descent, you have some function f of x, right? And here we're looking for the optimum. So this x star that has minimum f, minimum loss. And we initialize somewhere and we want to compute a minimum. So we define the gradient. I have not defined it yet, so here it is. This is the gradient of f. It is just the, oh sorry, this should be f, this shouldn't be g. I apologize, obviously this should be f. It's a copy-paste mistake. So this is the derivative of f with respect to all the individual entries of x. X is typically some high-dimensional vector. Could be hundreds, thousands, millions of weights, right? So it's a very long vector of the partial derivatives, and that is called the gradient. This is a vector that has the dimension of your input space, right? So if your input space has hundreds of weights, then your vector is hundreds dimensional. And this is a vector that points in direction of the greatest increase of the function. And so in gradient descent, you would take steps in direction of the negative gradient. That is the direction of steepest decrease. And so here I showed this again. You have an initial value x, you have the gradient vector at that location x, and then you would define, if this is xt, let's say, then xt plus 1 is xt minus some learning rate times the gradient at the previous location xt. So here the index t and t plus 1, this is the vector over time. So you have to be careful. At this point x has two indices. One is the lower index, that is basically the component of x if it's a high dimensional vector, and the upper index is the time index in the gradient descent. So you shouldn't mix these. And so if you update this stepping, then for t going to infinity, you would get an optimal solution that would be the nearest local minimum. I say nearest local, that's not necessarily true, but the local minimum in the descent direction, whatever you find there, right? People often say nearest local minimum, but obviously if you have x here, right, and then you have a loss function that looks like so, and you initialize here, then the nearest x0 is your initialization. The nearest minimum is this one, but the gradient descent will obviously lead you somewhere else, right? So just assuming if you initialize close to the right solution, you will find it is not necessarily the case, right? So if this is where you wanted to go and you initialize here, you might be going in the wrong direction. So. But it's pretty obvious where the gradient descent will take you. Some local minimum. Now let's go back to neural networks. Here is a bigger neural network with L layers, M neurons, and for simplicity we assume it's the same number of neurons per layer, but as I said, it doesn't have to be. And then we can define the gradient vector, and that can be big, right? So it will contain the derivative of my loss, or of my loss in general, with respect to all the unknown weights. 0, 0, 0 to LMN, where L is the number of the layer, M is the neuron in this layer, and N refers to the input that it gets from whatever previous layer. Right? So the number of N depends on how many neurons you had in the previous layer. And then you can define a gradient step, which means you say, update my weight matrix, the set of weights, according to the gradient with respect to all these weights. And these graphs can be huge. They can be large. This is an example from a project at Google that was called Going Deeper with Convolutional Networks in 2015. And then there was a paper called Very Deep Networks that was, I think, even deeper, right? So they, people started using hundreds and hundreds of layers and often very complicated, not complicated, but a multitude of processing steps that involve convolutions, that involve average pooling, max pooling, concatenation, dropout. You can see, we'll talk about a lot of these later in class, but there is a lot of different things you can, processing steps that have been shown to work well in neural networks for various application tasks. And it's nice that, these graphs will often allow you to visualize graphically what you're doing. So even though, if you were to write this out as a mathematical expression, the reader would be hopelessly lost. But in this graphical visualization, you still have some overview of what's happening, roughly. It's an interesting thing, especially politicians and the public, they're now very keen on explainable AI, right? And they want everything to be explainable. And for me, the question is always, is that sufficient of an explanation to you? If it is, then we're good. If not, then... it's not easy to make it more explainable than this, than saying there is a lot of processing steps that happen from the input to the output. So you can say the neural network is not a black box, but inside, that's what it looks like, Face it, that's life, right? If that's not a good explanation, then I'm not sure we can get into business, right? And so if you concatenate all of these nodes, you get some big neural network. And the idea is that you have the neurons and that you have these forward and backward passes. And so we can actually look into one single neuron and see how that looks. So we have some input to the neuron, we have some output, and the neuron does some processing. And what's nice is that we have respective software libraries like PyTorch and TensorFlow that we can use to optimize these network architectures. So each neuron gets some activations from the previous layer, and then it has an activation function, and then there is an output Z, and then you can backpropagate through this network and compute derivatives. And typically partial derivatives with respect to the various inputs here, X and Y. And then you have chain rules, so you take in the backpropagation for each neuron in the compute graph, you take the derivative that you get in from the right and you multiply it with the partial derivative of Z with respect to X or Z with respect to Y in this case, right? And then you continue backpropagating. And so this is what this information flow for computing derivatives looks like for individual neurons. Here's a simple example how gradient descent works for neural networks. Here, as you can see, we have one input layer, we have one hidden layer in blue, and we have the green output layer, 0, 1, y hat 0 and y hat 1 is the output. And then we have a loss function. For simplicity here, we'll choose a mean square error loss. but you can choose any other loss if you like. The mean square error is popular because it's simple and because derivatives are easily computed. But the thing is, no matter what you do for pretty much any expression, you can define and compute derivatives, and then it's just standard processing. So we have ground truth labels for 0 and 1, and we can measure the discrepancy in terms of the mean square error. And we have these hidden activations, HI we call them, from 0 to 3. So how many weights do we have in this network? Well, that's the first thing. If you want to, train a neural network, you have to determine how many unknowns do I have. That's easy. The weights are just all the edges. For every edge, there is a weight. How much the output of x0 is with what weight is it aggregated in the input to h0. And so since there is 3 neurons in the input layer and 4 in the hidden layer, there's already 3 times 4, 12 weights here, and 4 times 2, namely 8 weights there. And then we have respective biases, if you want. And so we have, 8 and 12 is 20 weights W, and then a set of biases accordingly. For every neuron, there is a bias. And as nonlinearity here, we'll choose a simple ReLU. So this max 0x, that is the rectified linear unit that we've seen many times already. And now we can go ahead and do computations. So for computing the derivative of the loss with respect to the weights, let's say in the first layer, in the hidden layer, these weights here of these, you would do dl by dy and then dy by dw. dl by dy, since it's a mean square error loss that we use, it's just 2 times yi minus yi hat minus yi. And then dw, dy I hat by dw, since this is a linear weight, it's just hj. It's the output of the previous layer, basically. And that is if it's positive. Why? Because we have the rectified linear unit that is 0 for negative, so the derivative is 0, and for positive values it's x, right? So this function here, the derivative, if x is positive, derivative is 1. If x is negative, the derivative is 0, right? So it's just a step function. The rectified linear, if you take the derivative, it's a step function, a 0, 1 function. And so this is what you get here. And so that way you can do this layer by layer. So that would, multiplying these together will give you the gradient with respect to the weights of the hidden layer, from the hidden layer, and then the derivative with respect to the initial weights here, these 12 weights, you do dl by dy hat by dh, and then dh by dw 0, etc. And so that way you can compute all these derivatives, layer by layer. And that will give you the update step for your weights in the learning, right? How many unknowns do we have? We saw it before. The output layer has 2 times 4 weights W and 2 biases because it's 2 neurons, output neurons. And the hidden layer has 4 times 3 input weights and 4 biases. As I mentioned, you can consider activation functions that are more complicated than ReLU, for example, parametric ones, and then you would have some weights associated with each activation. And then you can say they should all have the same activation function, or each could have a different activation function. So you can see you can make things more and more complex. You can add a lot of parameters to give the network more flexibility. And there is a big discussion in the literature whether, activation functions should have parameters or whether they should not. I don't have a clear, there is no clear yes or no answer to this. It very much depends, and sometimes, and this is a little bit unfortunate on that level, research in the neural network world is to some extent trial and error. People try different parameterizations and see how far they get. And very often, the right solution is determined by whatever gives you the best performance, right? It's not very pretty for someone who has a more scientific approach to things, right? Trial and error is usually not the best way to do things, but we live to some extent still in a trial and error world when it comes to neural networks. You can do the same for the cross-entropy loss. We started with the mean square error loss because things are simple, but for the cross-entropy loss that we've seen for multi-class classification, this is it, right? So this is the binary cross-entropy loss, and we saw that you can generalize it to multiple classes as well. But let's start with the binary cross-entropy loss, and then we have a sigmoidal nonlinearity here that allows us to predict a class label, and then we have these scores SI. And it's the same idea that we can apply here, standard derivative rules, a number of terms cancel. In the end, it's fairly simple gradients that we'll get, you'll see. So here we do chain rule, to determine the derivative with respect to the weights. Here's the chain rule. And then for each expression, we have to compute the derivative. Here, for example, this is the derivative of this expression. It looks a little bit complicated, but it's very standard derivative computations. How do you evaluate the derivative of the logarithm with respect to y hat? And this is typically 1 over y hat. So this is what gives you this term and that term, and you can basically put them together. You get this expression. And then dy by ds, since we have a sigmoidal here, this is what it looks like. And then ds by dw, since this is linear in w, we just get hj. And then then you have to put it all together, and then the derivative with respect to the weights is given by this expression. And sometimes it helps, once you've done all these computations, it helps to look at the output and see, does that make sense? Is that reasonable? I always recommend doing that if you can, because that allows you to, to debug whether you've done things right. Here, for example, what you see is the update in the weights depends on whether the prediction is larger than what it should be or whether it's smaller than it should be. And you can see the prediction is 0, the update of the weights is 0, because we update the weights according to the gradient, right? This update is 0 if and only if the prediction and the target are identical. Then the difference is 0, and then the weights don't need update because the prediction is perfect. And as soon as the prediction is too large with a negative gradient, it will make sure that it gets smaller, and vice versa, right? And same for here, right? So this is actually quite interesting to see that this behavior that we see in this gradient vector is, quite sensible. We can also, so that was for the 0 layer, right? The derivatives for the 0 layer. Here is the derivatives for the first layer. Sorry, this is for the hidden layer, I should say, the last layer. Sorry. These weights of here. We can do the same for the weights of the previous layer, and in the same way we have to backpropagate through the whole network, right? So we do dl by dHj is this expression, dl by dy, dy ds, dy hat ds, ds dh, right? And then we plug in all that we found on the previous slide, and we get this expression. And then we can say so basically this is then dl by ds is dl by dsi times dsi dsj. So this is the activation of the one layer times then the derivative with respect to the previous one. And if you concatenate all, you get these somewhat lengthy expressions. So these expressions look complicated, and they are sometimes, especially if you have hundreds of layers, they will get arbitrarily complicated. And this is why we have these compute graphs where you actually don't do the analytical calculation end to end, but you propagate layer by layer and you process layer by layer, and then it's just a standard recipe. And this is what these software libraries provide. So back to compute graphs, how does that work? We have inputs x and y here, where x is what should be processed, and y is the ground truth. And then we have a two-layer neural network for regression with a rectified linear activation. So this is what it looks like. 2 layers means I first multiply by the weights of the first layer, then ReLU, then weights of the second layer, and then I have a mean square error loss with respect to the ground truth. That's the problem I consider. So you see, we consider problems of different levels of complexity. We show the compute graph that it corresponds to, and then we can do gradient descent. We initialize with, let's say, 1, 0, right? And the weights W1 and W2 we initialize with 1/3 and 2. You can choose different ones, doesn't really matter. Then we have the loss, and then we can do the computing. So we take the derivative of the loss with respect to y hat, since its mean square is just a linear function in y. Then y hat is W2 times the output of the previous layer, and so dy hat by dw is the output of the previous layer, sigma. And so we can do a forward pass here through the network with these initial sets. We get the loss, and then we can do, given these partial derivatives, we can do backpropagation. The derivative of the loss with respect to W2, we have to first take the derivative with respect to y hat, and then y hat by W2. And much like I showed you before, you can then propagate these values back down the chain, and you just have to insert the derivative evaluated at the respective location. And that's how you can propagate down, and you end up with 4/9 as the derivative of the loss with respect to the weight W2. And along the same vein, I can do the derivative with respect to the weight W1. So please try this at home, do this for these and other compute graphs, so that you get a little bit of experience of how to work with compute graphs. And as you can see, it's not difficult, it's just chain rule, and each expression has to be multiplied with the previous expression, as you can see here, right? And so we do this numerical evaluation, and as I mentioned, on a GPU, this even for very large network architectures, that can be done rather efficiently. It can be done rather efficiently, but the issue is, and this is the biggest nuisance in training neural networks, is that you typically have to do thousands of iterations update the weights, and go again. So you constantly backpropagate through these compute graphs, and even though this can be done efficiently, you don't want to do too many iterations. And as we mentioned before, the key challenge is how do we choose the step size, the learning rate, so that we do sufficiently large updates, but updates that are not too large. And this is challenging. You want to do larger steps, but you don't want to overshoot. As I mentioned, if you do too large steps, then if this is your loss, and you start here, then you go here, and then you go back, and then you go forward and back, and then the thing will zigzag constantly, and this is not so easy. One question being, how do you detect that you just overshooted, right? That you just overshot, right? You start here and you end up there. The loss is smaller than what it was before, but you went too far. How can you even detect that, right? Sometimes what you can do is you can look at the weight space, and then you will see in the space of weights somehow I'm zigzagging. That's not a good sign either. So not only do you want the loss to grow smaller with each iteration, but also you don't want any zigzagging in the solution space, right? And so there are ways to visualize a little bit what's happening to make sure that you don't overshoot. And so in this fashion, I can compute derivatives here, numerical derivatives with respect to the various weights, and then I can update the weights like we saw and say the new weight vector is the old weight vector minus learning rate times gradient. And then I can do that in this case. For example, 8/3 and 4/9 were the two derivatives that we ended up here, the partial derivatives that are then stored here. And these I plug into the gradient vector, and I update the old set of weights and get the new set of weights, and then I iterate. But how do we choose a learning rate? It's tricky. It's not easy. In principle, you can do this gradient computation for each single training pair, right? Because we have gazillions of training data. For each, each gives us an X and a Y, and thereby we can see how well does the prediction of for X fit to the ground truth Y, and that gives us a training signal that we can use to backpropagate, to update the weights so that this training pair is better classified, right? But the question is, how do we do that for a large training set where we have potentially hundreds and thousands of images? And in principle, that is fairly straightforward. As we said, the loss function can be defined as the sum over the losses for all training samples, and hence the gradient is the sum of the gradients for all training samples, right? The question, though, is can you do this if you have millions of training samples? Is that efficient? And one question is, typically the summation over all training samples is just not feasible computationally. And the question is that the most efficient way to go sample by sample or to try to sum over all samples? And what we find is there is elegant ways to speed things up. And this is what we'll talk about in the next lectures. And this is often what's referred to as stochastic gradient descent, where rather than taking all the training samples, you take batches of subsets of the training samples and you compute the gradient for these, and then you update, and then you take a new subset. It's called stochastic because you don't take all the samples but some random subset. But before we get into stochastic gradient descent, we do want to talk a little bit more about what's called regularization. And that's what we're going to do next week. Thank you very much.